Thank you for the introduction. I'm Haibo. I'm happy to present our work, which is trying to use the PMU to detect and identify security attacks. So first, I want to convince that software security matters. Actually, there are a couple of papers in the morning session. And software security, we are called economy, effects, and social impact. So we are called lots of billions of money, and people can correlate one. But software vulnerabilities is inevitable. I remember in the last talk of this morning says that every bugs in kernel will somewhat turn to a security vulnerability. So current way of detecting attacks, most of them are based on instrumentation and compilation, or some requires dedicated hardware. So in this talk, we are trying to make a case for using performance counters to rescue. So performance counters is pervasively available in commodity processors. So, and we all know that it's non-intrusive. We do not need special modifications programs in order to use counters, and it's commercially available, and it's usually with very good performance. So if we use performance counters to detect attacks, we made an observation that there are actually some performance invariants inside programs. So if we liberate these performance environments and observe the performance samples obtained by PMU, then we could do some performance diagnosis and intrusion detections. So this means that we do not require special hardware and requires no source code modifications. So so let's see a real-world examples of Samba. There is a heap overflow in Samba server. So the original server, there is heap overflow, and there are the destructors in the heap. If there is some shell code which do some heap overflow and modify the destructors to some shell code, then the program will eventually transfer control to the shell code. So let's see what happens to the performance samples captured by PMU. So the y-axis is the number of occurrence of performance samples, and the y-axis is the virtual addresses. So we can see that this line shows the normal run. We could also only see instruction TLB misses in this address range. But if this program will get attacked, we could see performance samples in both this address range and this address range, which should not appear in normal execution. So we could use this sense as a possible evidence of possible attacks. So in this case, we only use instruction TLB miss as evidence. Let's see what PMU provide and what's the problem with traditional PMUs to do intrusion detections. So the traditional performance counters monitoring unit is usually imprecise. What we remember of performance counters is that it's usually using some sampling-based techniques, and it's usually imprecise. I remember there's a paper states that in AMD and Intel machines, the instruction point sampled it can get to like 72 instructions away from the real instruction point. But unfortunately, the hardware vendors had provided some advanced performance counter features. So currently they can do some precise sampling. Like in Intel, they have a PEPS called precise event-based sampling. And the IBS from AMD called instruction-based sampling, which can capture the exact instruction point of the sample's happens. They also have some advanced features like branch tracing. For example, Intel have branch trace store. So the cool things of branch trace store is that it has some predefined buffers to capture all control transfers, such as real jumps, far jumps, function calls. So we could have the complete control flow of our program. So they also have predefined buffers to store branch record. So we do not need to raise or interrupt when one single performance samples get captured. So we only need to raise or interrupt when the buffer is full. So this means that the branch trace could have a very low overhead. So the opportunity is that we have the entire control flow, and we might know that many of security breaches are actually related to breaches in control flow. So we could check the anomaly in control flows to detect attacks. And we could also do a complete backtracing to diagnose the performance attacks. For example, we can backtrace the security of exploits, and we know how the program gets to this shell code. So let's have an example of commercial processor supports for PMUs. So most processors have imprecise performance counters. And recently, some modern processors have the precise event-based sampling, like Intel Pentium 4 Core and i7. They also have some branch trace store in the newer processors. Also in i10 2, they have branch trace buffer, which is similar to branch trace store. So we can use PEPs to get a more accurate information of the performance samples, and we could use branch trace store to get backtrace of the control transfers. So by using these performance counter features, we could detect several kinds of security exploits. So this column depicts the PMU events, and this column depicts the attacks that can be detected. So for code injection attacks, we can use branch trace store and the branch mispredictions and the instruction TLB misses. This is because in normal execution, most of the these events like branch misprediction and the instruction TLB misses are only happen in the code section. They will never happen in the section. And we could also use branch trace buffer and branch trace store to detect some return to Libc attacks and the return-oriented programs, which will break the control flow integrity of the program. So we could use branch trace store to capture all these kind of attacks. So let's first show how we could use branch trace store to capture return-oriented attacks. So in return-oriented attacks recently emerged. So the cool features of return-oriented program is that it does not require the attacks to inject shell code into a program. But it reused the existing code, existing instructions in code to form a shell code. For example, if supposed to execute the instruction 1, 2, 3, and they do a return, it's by forging a stack and jump into this, and then execute the instruction 5.